Okay, good morning, everybody. So today we'll continue our discussion about areas in polar coordinates. So I'm thinking we still have one lab class, which would be on Monday, the last day of classes. So perhaps then we can talk about parametric curves. So did you finish talking about it in the lecture today? I guess that's why you were a bit over time in the lecture. Mm-hmm. Okay, sure. Herson, yeah, I can go over that after this one. So, all right. Okay, you finished 10.4. Let's just defer our discussion about 10.4 to Monday. So today we'll focus more on more examples on using integrals to find the areas of polar curves, because I guess it's more important, or this topic is much more heavier than um, parametric curves. So we can do that on Monday. So I think this is one problem one of you sent last time, but it was towards the end of the class. So I discussed it in a bit of a hurry. But let's redo the solution, because I also encountered a lot of students in my CASA tutorials asking for help in this particular problem. So here we need to find the points of intersection of the polar curves r equals 9 sine 2 theta and r equals 9 sine theta in Cartesian coordinates. So I guess the setup should be natural to you guys, because here we need to find the POIs, the points of intersection. You see the first curve is r equals 9 sine 2 theta. The other curve is r equals 9 sine theta. Both right-hand sides are equal to r. So you can start your solution by putting those right-hand sides equal to each other, because they are both equal to r. So we want to find what is the theta value at which they intersect, or when they will have the same r value, right? So our first step is to do 9 sine 2 theta equals 9 sine theta. And of course, you can divide both sides by 9. So you'll have sine 2 theta equals sine theta. And this is where most students got stuck. This is something that you have encountered in pre-calculus or trigonometry, which might be a little while ago, so we need to review a little bit. So whenever solving trig equations, you want to isolate the trig function on one side of your equation. But that would be a little bit difficult here, because you have two different angles inside your sine function. So the left-hand side has a 2 theta inside the sine, and here you have a theta inside the sine. So what you can do is to use identities to make the angles inside the trig functions the same. So for the left-hand side, I can use a double angle identity. So if you go back to your pre-cal notes, you will see that sine 2 theta is equal to 2 sine theta cosine theta, which is a good reminder that you need to at least review these basic identities for solving for points of intersection, right? So this is what I'm telling you since the beginning of the class, that math is a sequential course. So you probably will need things that you have learned in previous classes in more advanced ones, right? So now, okay, so now we have thetas inside the trig function. So what I can do is to transfer the sine theta to the left side. So I'll have 2 sine theta cosine theta minus sine theta equals 0. Remember, for equations, we don't divide both sides by sine theta, because sine theta could be 0. So you might be missing one of the solutions. So the safest way is to make one side equal to 0, right? And then we can factor out the sine theta. So we'll have sine theta times 2 cosine theta minus 1 equals 0. We have a product of two numbers being equal to 0. That means either of the factors is equal to 0, right? 2 cosine theta minus 1 equals 0. And sine theta is 0 when theta is 0 or pi, right? At least on the fundamental solution set. Or here we get cosine theta equals 1/2. So when is cosine equal to 1/2? So we go back to the unit circle. Cosine is 1/2 at pi over 3, and the other one would be at 5 pi over 3. Okay, yeah, great, Herson. Yeah, that's correct. So these are the theta values where we know that the two graphs will intersect. But if we go back to the problem, we need to find the points of intersection, and not just the points of intersection, but we want them to be expressed in Cartesian coordinates. But in order to find the points, we need to find the actual points in polar and then convert it into Cartesian, right? So here we know the theta values where they will intersect, right? 0, pi, pi over 3, and 5 pi over 3. To complete the picture, let's compute the r components, all right, of these points of intersection. Well, you can either use this formula for r or this equation for r. Either way, you'll get the same answer. So I'll pick the easier one. So I'll use this to evaluate the r component. So again, you could have chosen 9 sine 2 theta. We know that at the points of intersection, they will have the same r values, right? So plug in theta equals 0. I'll get 0 here. I'll get 0 here. And then sine of pi over 3 is root 3 over 2. So that's going to be sine of pi over 3. That's 9 root 3 over 2. Right? And then sine of 5 pi over 3 is negative root 3 over 2. Remember, there's a multiplier 9 for our function r. So here we have the points of intersection. So POIs are the pole 0, 0. Now I'm using square brackets because these points are given in polar coordinates. Okay, and then it happened that these guys are the same point. So only one point of intersection for those two theta values. And then we have 9 root 3 over 2 at pi over 3. And we have negative 9 root 3 over 2 comma 5 pi over 3. Okay. So these are our points of intersection, but these are expressed in Cartesian in polar coordinates. We need to convert it into Cartesian coordinates because that's what the problem is looking for. So note, the pole is identical to the origin in Cartesian coordinates. So we don't need to do much of a calculation there. Okay. Now we'll convert the other 2 points. So here we have the first point of intersection. The second one is computed. The x and y components are computed as r cosine theta and r sine theta respectively, right? So for the second point, we use these two guys for r and theta, right? So for the second point of intersection, we have 9 root 3 over 2 times cosine of pi over 3, which is what? This would be 9 root 3 over 4. And this guy would be 9 root 3 over 2 times sine of pi over 3. So that's going to be 9 times 3 all over, sine of pi over 3 is what? Root 3 over 2, right? So this would be 9 times 3 over 4. So this would be 27 over 4. So the second point of intersection in Cartesian polar is 9 root 3 over 2 comma pi over 3. But in Cartesian, it's going to be 9 root 3 over 4 comma 27 over 4. Right? Remember, I'm using parentheses for the Cartesian coordinates. All right. Do you guys agree? Are my calculations correct of the trig function values? Right. Then we need to do this for the last point, right? So the last point of intersection is this. So we compute for the x component. Again, this is r cosine theta. So that's going to be negative 9 root 3 over 2 times cosine of 5 pi over 3. That's negative 9 root 3 over 2. Cosine of 5 pi over 3 is 1/2. So the x component is negative 9 root 3 over 4. And the y component is r sine theta. So this is minus 9 root 3 over 2. Sine of 5 pi over 3. Or sine of 5 pi over 3 would be negative root 3 over 2. So minus 9 root 3 over 2 times negative root 3 over 2. So that's going to be 27 over 4. So the last point of intersection will have Cartesian coordinates negative 9 root 3 over 4, comma 27 over 4. Okay, guys. All right. Now, I hope that helps because I think in your quizzes, there's a lot of questions pertaining to finding points of intersection, but be careful. Most of them will not ask or will not just ask for the POIs in polar, but they will ask you to convert them into Cartesian coordinates, right? Oh, by the way, guys, we finished grading your FRQs yesterday, so expect to have it over the weekend, probably Monday at the earliest. The scores are not that it's not as high as previous classes, at least for the papers I graded. Yeah, I only got only one person who got a perfect score. So I guess the last exam was really tough. So hopefully you'll make up for it on the final exam. All right. Okay, let me go to Hersons question. Let's call it problem 5. So you want to calculate the area of the region bounded by r equals 8 cosine theta, r equals sine theta, r equals 8 sine theta, and the raise theta equals 0 and theta equals pi over 4. I think here we need to split the region of integration, especially the last one. Yeah, the last problem was finding the Taylor series expansion for a function. You're given the derivatives, but you're asked to find the expansion for a constant times f of 2x or f of 3x, right? I want to comment on the usual mistakes that I found or usual problems students face during the FRQs, but I'm not sure if I can do that today because some students might not have taken the exam yet. So I'll keep my mouth shut for today. Probably on Monday I can give you some notes about it. All right, so yeah, the rays are just bound for the polar curves. Yeah, that's right, Herson. I'm guessing your theta equals 0 and theta equals 4 will serve as your bounds for the integration. But as always, it's better to have a picture or a sketch of the region so you exactly know where you want to integrate, especially for polar curves, because often polar curves doesn't appear to be as obvious, or the points of intersection are not that obvious. Because one difficulty is that even if, say, okay, say this is your polar curve, right? So if you have this point, it is not necessary that this is your theta value, or the theta value used, because the theta value might be here, but you have a negative r value. So we need to be a little careful in dealing with polar curves because they do not appear exactly as how they are drawn, or they do not behave exactly as how they are drawn, because the angles are affected by the value of r being positive or negative. So let's see. Okay, let's sketch the graph. So the first function is r equals 8 cosine theta. This is a circle tangent to the pole. And since you have a cosine, so this will primarily be along the x-axis. Since the coefficient is positive 8, it would be a circle tangent to the pole, oops, but lying primarily on the positive axis or positive x-axis with diameter 8, right? So again, I knew that r equals a sine theta or a cosine theta are circles tangent to the pole. I look at the trig function involved, it's a cosine. So I know this would be a circle tangent to the pole, either on the positive x-axis or the negative x-axis, because it's a cosine. Cosines are always associated with a variable x, right? And then the coefficient is positive 8, so that means the circle should be here, right? If it was a minus 8, then your circle will look like that, right? So here we have a circle of radius 8. Oh, sorry, of diameter 8, right? This would be 8 units, okay? And then the other circle is 8 sine theta. It has a sine, so it's either primarily on the positive y-axis or on the negative y-axis. But since the coefficient is positive 8, it will be on the positive y-axis. Right, so it should be somewhere here. Let's extend. Okay, there we go. And then the rays. I should have used a different color for this. Okay, hold on. Okay, and then the rays are theta equals 0. So here's your theta equals 0. Oops, what am I doing? So this is theta equals 0, and theta equals pi over 4 should be somewhere here. Okay, so now let's identify what is the region. So the region is said to be bounded by the 2 circles and the 2 rays. So it should be bounded by the 2 circles and the 2 rays. So basically that would be, why do we have pi over 4? Yeah, let me reread the problem. Probably that's also the difficulty here Herson encountered. Calculate the area of the region bounded by the 2 circles and the rays theta equals 0 and theta equals pi over 4. So the bounds are fine, but it should be bounded by the 2 circles. But do I find... Okay, so that means the region should be this. Right? Because it should be bounded by the 2 circles and the 2 rays. So this guy is your circle, the red circle. This is the bound corresponding to the black circle. This is your ray. This is your ray. So the region would be this. Okay, is that clear? Yeah, sometimes they can be tricky, especially if you look at the rays. So we need to be a little careful with that. Okay, then let's set up the integral. So here, yeah, that's also my first instinct. You mean, I was thinking about this guy. Oops. Yeah, evaluating this. But I realized it is not bounded by the black circle at all, right? It doesn't touch the black circle at all, except possibly at that single point there and at the pole, right? So it doesn't count as being bounded by the black circle. So we need to go over here, all right? So now the area would be, okay, area. There's a mainstay 1/2 integral. Let me put it here, okay? For the bounds, well, we know that the region starts from theta equals 0 until pi over 4. 0 until pi over 4. And then the integrand would be the sort of radius squared, right? But how do we identify what should be the integrand? Well, what you can do is draw a ray Okay, which would be, and then do a little experiment here. Hold on, let me delete this one. All right. And then see what happens when this green ray is being radiated over the angular span. So what happens when that ray goes from theta equals 0 until pi over 4? And see what is the inner and the outer radius, right? So, okay, if my ray is here, my outer radius is the black circle, and the inner radius is the red circle. If I go here a little bit, okay, now still, the outer radius is the black circle, the inner radius is the red circle. And then if I continue traveling from 0 until pi over 4, I see that that is uniform. That is the uniform behavior all throughout 0 to pi over 4. So from theta equals 0 until theta equals pi over 4, the inner radius is the red circle, and the outer radius is the black circle. So I don't need to split the integral up. And that's the thing. In rectangular coordinates, we use horizontal or vertical strips, slide it to the left and to the right, up and down to find what's the upper and the lower, or the right and the left. For polar curves, what we do is think of it as a hand of the clock, but traveling counterclockwise, and see what is the inside radius and what's the outside radius, right? And all throughout 0 to pi over 4, my outer radius is the black circle, which is 8 cosine theta. But remember, the formula calls for radius squared minus the inner radius squared, that's the red circle, 8 sine squared theta, all right? D theta. All right, and that's going to be your area. Let's try to evaluate, because you were told to evaluate or to compute the area. So we need to remember how to evaluate integrals involving trig functions. So this would be 0 to pi over 4 of 64 cosine squared theta minus, oops, I have a typo here. The square should be right outside the entire r. So this would be minus 64 sine squared theta, all multiplied by d theta. And then I can factor out the 64 all the way out of the integral. So 64 over 2 is 32. Integral from 0 to pi over 4 of cosine squared theta minus sine squared theta. Don't forget to enclose them in parentheses. There we go. And then to evaluate this, you can either use the half angle identity, or how we dealt with even powers of sines from techniques of integration. I think that's chapter 7 or 8, correct? Or you can take advantage of some identities from trigonometry. So cosine squared theta minus sine squared theta, I think, is cosine 2 theta, d theta. And here I will let u to be equal to 2 theta. Du will be equal to 2 d theta, right? Or d theta will be replaced by du over 2. So I'll have cosine u times du over 2. And then the bounds would be from 0 until here theta is pi over 4. So u would be 2 times pi over 4. So that's going to be pi over 2. And so this would be 16. Integral of cosine is sine u, evaluated from 0 to pi over 2. It's going to be 16 times sine of pi over 2 minus sine of 0. So that's going to be 16, right? So the area is 16 square units. All right. I hope that helped. Yeah, you need to be very careful, especially in determining what the shaded region is, because the rest of your solution is dependent on the sketch of the region. But luckily in the exams, this is one thing that you can take a look at, because we were told that remember, the exams have multiple parts, right? A certain question might have several subparts. So if you messed up on the first part and you used your result in the first part, which was wrong, in your solution in part B, then if you do the process correctly for part B, then you should get all the points for part B, all right? So I suggest you, when you get your FRQs, take a look at that, right? Just to make sure that it was graded fairly, because that's what we were told to do, right? So if your answer is wrong in part A, and that is used in part B, if you did the process for part B correctly, even if you used the wrong answer you got from part A, then you should get the full points for part B. All right. Yeah, Herson, the most difficult and actually the most crucial part of this is sketching the graph, right? So let's try some more examples then, just to familiarize ourselves with sketching the graphs of these polar curves. Let's try problem 6. Let's try this one. The region inside, I'll just set up the integral. R equals 3 plus 2 sine theta. And the outside, R equals 2, right? So again, we start with sketching the graph, right? Let's identify what graphs do we have. So for the first one, we have R equals 3 plus 2 sine theta. This is a Limassons, right? And then for Limassons, we need to identify what type of Limassons do we have, right? So here we have A over B is equal to 3 over 2, which is greater than 1, but less than 2. So we have a dimpled Limassons. Yeah, probably I'll just pronounce it as a Limassons. And yeah, forget about imitating a French accent there, or is it French? Limassons. But yeah, let's just call it Limassons. It's quite hard to pronounce it that way. Okay. So for Limassons, what we do is probably to make a table of values for any Limasson. So we take we make a table of values for the 4 quadrantal angles, and then based on the expected type of Limassons, then we can draw the graph properly. So here I'll make a theta R table. And for the thetas, I will just pick the quadrantal angles. 0, pi over 2, pi, 3 pi over 2, and then I'll do 2 pi as well, all right, just to complete the picture. And then plug these theta values into our Limassons, all right? So theta equals 0, so we get 3. Pi over 2, we get 1, so 3 plus 2, so that's going to be a 5. Sine of pi is 0, so we'll get a 3. 3 pi over 2 plug in here will give us -1, so -2. 3 minus 2, that's 1. And a 2 pi will just repeat the value for 0, right? Because our function is, that's a complete revolution in the unit circle, right? So here, let's, oops. Okay, let me just copy this so I don't have to draw it every time. Okay. And then, all right, so I need how many radial values? I will have 3 radial values. So just to guide me, let me draw 3 concentric circles. Oops. That's radius 1. This guy would be radius 3. And this guy would be radius 5. Okay. Come on. Go in the middle. There you go. All right. So when theta is 0, we are here. The radius value is 3. So let's label it 1, 2, 3. So we have the first point would be not 1, 2, 3. These are 1, 3, 5. Oops. 1, 3. Come on. You already know it's almost the weekend because I'm messing things up here. Okay, I'll just keep that there. So, okay, when theta is 0, the radius is 3, so that's our point. At pi over 2, we are here. The radius is 5, so I'll go to the outermost circle, right? At pi, the radius is 3, so here's pi. Radius is 3, so we are there. And then at 3 pi over 2, our value is 1, so this is 3 pi over 2. Go to the smallest circle. There we go. And then back to theta equals pi over 3. All right. And then we are expecting a Limassons with a dimple, so it should look like this. And then you have a sign here with a positive coefficient. So the majority of this Limassons will lie on the positive y-axis, right? Y-axis, because you have a sign, the coefficient of sign is positive. So that means it's on the positive y-axis. So our Limassons will look like something like that. Let me draw it here. So okay. All right, so that's your dimpled Limassons. Let me just try to salvage this picture. This is one time that my students are always making fun of me when I'm drawing this graphs. Oh, there's another one when I'm drawing three-dimensional graphs. All right, so there we go. That's our Limassons with a dimple. Now, the other one is r equals 2, so that's easy. That's just the circle of radius 2. So here's what we got. Circle of radius 2. That's r equals 2, right? So this is r equals 2. And this is r equals 3 plus 2 sine theta. All right? And we want to find the area of the region inside the Limassons, but outside the circle. So maybe I could erase the guide circles there. So we want inside the Limassons, but outside the circle. So the shaded region would be this. All right. Outside the circle, inside the Limassons. Now, when will we start the integration? Well, the integration should start here at that point of intersection, at that theta value, right? But we don't know that. Let's call it alpha. And then it will end here at the other point of intersection. Let's call it beta. So we need to find alpha and beta, which are basically the theta values at the points of intersection. So let's solve for the POIs. So solve for the POIs. Okay. Now we have r equals 3 plus 2 sine theta. R equals 2. Both right-hand sides are equal to 2. Are equal to r. So let's put them equal to each other. So we have 3 plus 2 sine theta equals 2, right? This is our first r value for the Limassons. This is the r value for the circle. So we'll equate them to each other. So we'll get 2 sine theta equals -1. And sine theta is equal to -1/2. Now, what are the theta values when sine is -1/2? Well, sine would be -1/2 at 11 pi over 6 and 7 pi over 6. All right, those are the two angles whose sine is -1/2. Now, we need to be a little careful here because you cannot simply use this, you cannot use these two angles right away as your bounds for integration. Because remember, we should radiate all throughout the region. So, okay, you draw a ray that will pass through the region. And imagine this to be traveling like a hand, like the hand of a clock, but in the counterclockwise direction. So the integration actually will, the integration can start here, and then you rotate counterclockwise, and will end here, right? So that means this alpha should be my starting theta value. but it doesn't make sense to start at 11 pi over 6 and end up at 7 pi over 6, all right? So that means I need another representation for this alpha angle, right? So instead of 11 pi over 6, I'll call it negative pi over 6 and 7 pi over 6, right? Because the lower angle, the lower bound for your integral must be smaller than the upper bound, right? So the integration will start here, which will not make sense if we'll start at 11 pi over 6 going to 7 pi over 6, because 7 pi over 6 is obviously smaller than 11 pi over 6, right? So what I'll do is to represent this as 7 pi as negative pi over 6, travel in the counterclockwise direction. And note that as I travel in the counterclockwise direction, right, the inner radius is always the red curve, and the outer radius is always determined by the black curve, right? So that means my area is 1/2 our mainstay, all right, times the integral from the alpha value, which we know to be negative pi over 6 until 7 pi over 6, right? Then outer radius squared, 3 plus 2 sine theta, quantity squared, minus the inner radius, which is 2 quantity squared, right? Or maybe I could write it as 2 squared d theta, all right? Or you could also appeal to symmetry, because note that this is symmetric, or this region is symmetric with respect to the y-axis or the vertical axis. So you can just integrate from negative pi over 6 until pi over 2 and multiply your answer by 2, right? Because that's the beauty with polar curves. So an alternative solution here is 2 times 1/2 integral from negative pi over 6 to pi over 2 of the same function. Because here I took advantage of the symmetry. But note my angular span for the integration is just half of the original interval for theta. All right. Okay. Any questions? All good? So let's try another one. We still have time for 1 or 2 problems. Any questions so far, guys? No questions? Let me see what are the other examples I have here. Okay. Let's try problem 7. Okay, for problem 7, find all the POIs, or the points of intersection, of the curves r equals 2 cosine theta and r equals 1/2. Then find the area of the region inside the rows, but outside the circle. All right, so let's see. Okay, let's start by sketching the graph first and see what do we have here. Right, so here we have this curve, r equals 2 cosine 2 theta. There should have been a 2 here, right? So let's start with that. R equals 2 cosine 2 theta is a rose with 4 petals, right? Because here you have a cosine n theta, right? N is equal to 2, which is even. So whenever you have an even n, you need to multiply that by 2 to get the number of petals. So this is a rose with 4 petals, right? And then the base of the petals occur at the pole. That is when r is equal to 0. So it would be handy to know where are the bases of the petals. I mean, we know that that would be at the pole, but it would be nice to know what are the theta values wherein you are at the pole or at the base of the rows. So to find that, so we know that it would be at r equals 0, plug in r equals 0 here. So we'll have 2 cosine 2 theta equals 0, cosine 2 theta equals 0. And then here, what are the angles 2 theta, whose cosine is 0? So it's going to be at pi over 2, and then 3 pi over 2. But since we have a 2 theta, we need to go 2 revolutions. So the next one would be at 5 pi over 2. And the next one would be at 7 pi over 2. So that means theta is pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So that means that these angles, we are at the pole. So for instance, at pi over 4, so if this is theta equals pi over 4, we know that the point would be at the pole, right? At theta equals 3 pi over 4, which is here, will also be at the pole. At 5 pi over 4, the point would be at the pole, as well as 7 pi over 4. All right. So maybe I don't need this guys here just to illustrate the point. So you will be at the poles there, or at the pole there for those theta values. And then compute where the tips are. So the tips of the rows occur when r is equal to 1. When cosine, they will occur when your cosine, when your trig function is at its maximum, right? So the maximum value for cosine is equal to 1. So the tip would be the highest value. So the highest possible value is when your trig function is equal to 1, right? Actually, plus or minus 1. So those are where your tips are. Again, to find the tips, you equate the trig function to plus or minus 1. So the trig function is cosine 2 theta. I want to get the maximum and the minimum values because those will be the theta values where the tips would be, right? So I equate that to plus or minus 1. Let me write it properly. Okay. So what are the angles 2 theta such that cosine would be plus or minus 1? So cosine would be 1 at 0. And then it would be negative 1 at pi. Then it would be 1 again at 2 pi. And it would be negative 1 again at 3 pi. I needed 2 revolutions because my angle is 2 theta, right? Now I'll divide everything by 2 to get theta. So 0, pi over 2, pi, and 3 pi over 2. So that means that these values of theta, we have r equals cosine theta, or maybe let's make a table of values here. Okay, so these are our theta values: 0, pi over 2, pi, 3 pi over 2. Compute for r. So here I know that I'm gonna have 2. Plug in pi over 2 into your r equation. So let me copy this. Okay, so plug in pi over 2 here. So that would be cosine of pi. Cosine of pi is negative 1. So we'll be at negative 2. And then this would be 2. And then this would be negative 2. As expected, because they would be the highest possible values of r, right? Because by design, we equated the cosine to theta to its maximum and minimum values, right? So these angles, which happens to be the quadrants, we have this r values. So okay, so when r is 0, when theta is 0, we have 2. Maybe I need a guide circle here. So say this guide circle is of radius 2. Come on. Okay, there you go. That's radius 2, right? So when theta is 0, r is equal to 2. So this is my first point, okay? And then when theta is pi over 2, we are at negative 2. So theta is pi over 2, but r is negative 2, so we plot in the opposite direction. So this is my second point. Maybe I'll call it first point, second point. And then at 3 pi over 2, okay, sorry, at pi, r value is 2, so this would be my third point. And my fourth point would be when theta is 3 pi over 2, which is here. But r value is negative 2, so I need to plot it in the opposite direction. So I'll have the point there. All right. And then we need to trace this accordingly. So when theta is 0, we begin at here. But when theta increase, we'll have some values until it reach pi over 4, right? Because at pi over 4, we know that, why did it autocorrect? We know that at theta equals pi over 4, we will be at the pole, right? So theta equals 0 increases until pi over 4. Okay. And then from pi over 4 to 3 pi over 2, so we'll be here. And then we'll be here. And then we'll be here. Okay. And we'll close the pole there, right? So that would be, let me try this again. Okay, there you go. Okay, and then close it here. All right, so that would be your rose with 4 petals, all right? So you see how I trace it. I started at theta equals 0, increase theta until pi over 4, where we will hit the pole. And then I'll go to my second point, which is at theta equals pi over 2. Theta is pi over 2, then we will hit the pole at 3 pi over 4. And then from there, we'll go here at 3 pi over 2. And then we'll be at 7 pi over 4. Sorry, 5 pi over 4. And then at 3 pi over 2, we are here. Then we go here. So that's what I'm saying, that the polar curves doesn't appear to be or doesn't look like how they appear in the graph, which doesn't make sense. But basically here, you will be thinking that this point is obtained when theta is equal to pi over 2. But that's not correct, because this point is obtained when theta is equal to 3 pi over 2. That's why the proper sketching of the graph should start here, go here, and then go here, go there. And that would be the last point, because this point happened when theta equals 3 pi over 2, and then there we go. Okay. And then the other one is r equals 1/2. So let's draw r equals 1/2. Okay. Suppose this is r equals 1/2. Should be a little smaller. Oops. Okay, my figure is not drawn to scale, but I hope you get the idea. Now we want to get the area inside the rows, but outside the circle. So that means we're looking for this, guys. Inside the rows, but outside the circle. Okay. Oh, we need to find the points of intersection. All right. But it's already time. Give me 2 more minutes just to set up the things here. So solve for the POI. Okay. So for the POIs, we have r equals 1/2 and r equals 2 cosine 2 cosine 2 theta. So we equate them to each other. So we have 2 cosine 2 theta equals 1/2. So that means cosine 2 theta equals 1/4. I guess I made a typo here. It doesn't make sense that this would be my R value. R equals 1/2. I equate them to each other. I divide both sides by 2. But this would be not. This will not be exact. So maybe I should have used R equals 1 instead. Yeah. So let's change the problem again. That's the problem when I try to invent problems on the fly, because 1/4 is not a good, or it's not a special value for the unit circle. So I'll try to avoid that. So let's make R equals 1 here. And there we go. So you simply need to find the points of intersection. What are the angles? Theta, 2 theta, whose cosine is 1/2. And that occurs when you have pi over 3. And then it would be at 5 pi over 3. And then we'll have another revolution. So we'll have 7 pi over 3 and 9 pi over 3. Oh, hold on. Did I make the calculations right? No, this should be 11 pi over 3. All right. And then we divide both sides by 2. We get pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Let's see if that made sense. So that means this guy here, the first point of intersection here, is theta equals pi over 6. The next one is at 5 pi over 6, which is here. Oh, did we forget some things? Because there should be how many points of intersections? There should be 8 points of intersection. Why am I missing the other ones? Because I'll just be getting this, getting this, getting this, and getting this. Oh, sorry, I won't get this. Oops. Yeah, why am I not getting the other 4 points of intersection? Because I hope you see I'm expecting 8 points of intersection. 1, 2, 3, 4, 5, 6, 7, and 8. But why am I getting only 4? Because I should also consider the negative angles, right? But we're out of time, so I'll discuss this again on Monday with details to close up this to close our discussion about areas in polar curves. Because I hope you see the point. I'm missing the 4 other points of intersection because I guess I need to consider the negative angles, right? So we'll do that on Monday, and you guys have a good weekend. Bye, guys. See you on Monday.
Thank you.
You're welcome.